using 4 electrodes back here, but we're primarily looking at the back 2 electrodes of what we call O1 and O2. We use a simple gold cup electrode, surface mount electrode, so that it's easy applied and easy removed. A little bit of paste, and then that's all you have. The remaining 2 electrodes are behind each ear of the mastoid region. Again, the gold cup electrodes. A little bit of water, and she's all ready to go.
This military scientist is testing an interface that allows her to control a flight simulator merely by thinking. She's learned to alter her brainwaves, or EEG. These changes are picked up by the electrodes on her head and fed to the computer that controls the simulator.
The operator that you see in the simulator is Dr. Victoria Nessman, and she's one of the scientists that's working with us here on EEG-based control. And in a nutshell, what she's doing is she's controlling the motion of that simulator, performing a task by controlling the EEG activity in her brain. Now, specifically what's going on is that in front of Tori there's a light that's flickering 13 times a second, and that produces in her brain, in the visual part of her brain, what's known as a visual evoked response. So with biofeedback and training, what Tori has learned to do is to either make that response get larger, which causes the simulator to roll in one direction, or she can actually suppress her brain's response to the light, which causes the simulator to roll in the opposite direction. And you can actually see some of this control, I think, real nicely on this spectrum analyzer. For example, you see Tori produces a lot of alpha. That's this region here. But what we're concerned with is this spike that's indicated by this bright cursor. That's the controlling frequency. That's her response to the flickering light. And by raising or lowering it, that's how she controls the simulator. Now, what's interesting is as a person gets good at this, they do tend to think things like, I want to roll to the right, or I want to roll to the left, or I want to acquire this target on the right or on the left. So they do tend to associate thoughts with that, but we're not directly measuring a thought. You know, we can't tell what her desires or anything like that are based on what we're measuring.
Occasionally I might feel frustrated if the cursor doesn't do what I want it to do, but it's just a matter of trying again, and eventually it works. So it's less reliable than moving my arm, which I can do perfectly every time I want to do it, but my experience is pretty much the same. It's automatic, it's natural when it works.
You know, in the future, clearly you may expect some things like we see in science fiction movies, with computers that assist you with all aspects of your life, very, very intelligent robots and those kinds of things. And I think the alternative control work of the kind that we're doing is going to be a key element of that. For us to be comfortable communicating with these intelligent systems, then we're going to be able to need to communicate in ways that are natural to us, not ways that have been constrained because of limitations of the machines.
Our future relationship with machines may be very different from today's.
Self-assembly and biological molecules are really one and the same thing. Go look at yourself in a mirror sometime. I mean, after all, what are you made of? I mean, you ate something, you digested it down to fairly simple constituents, you have this enormous cellular machinery which built it back up. What are the forces that brought everything together? Why do you look the way you do? At a higher resolution picture, why do your cells look the way they do? At a still higher resolution picture, why does the nucleus of your cell look the way it does? Why do the membranes look the way they do? Why are the molecules in the membranes assembled the way they are? I mean, these are problems that are of great interest currently in biology, a problem that attracts me a great deal, and which I think many, many people find fascinating. It turns out many molecules self-assemble. We all know about soap bubbles. We've seen, the soap bubbles are made up of molecules that have some resemblance to what's inside a biological membrane, for example. And one sees these things spontaneously assemble and form interesting structures. There's a whole science, a growing science of molecular self-assembly. And so this is sort of building, perhaps the really important principle that one takes from biology is building things up from the inside out rather than from the outside in, which is more the tradition in conventional manufacturing. If you think about making something, you start with a block of something and you cut away at it. That's not the way biological systems are fabricated. They're fabricated from the building blocks and the pieces built up from the inside out. And perhaps there's a way to tie together these two things. "20 years ago, a student at the Massachusetts Institute of Technology
began to wonder what it might mean if we could manufacture things the way life does, and how it might change our world. The result of Drexler's 10-year study of molecular systems was a book. It's caused controversy in science ever since.
The reaction to Engines of Creation was mixed. There were members of the scientific and engineering community who read it and understood that there was a technical argument here, and were persuaded and said, yes, this makes sense. I think this is where technology is going. Gee, this is an important thing to understand. Other members of the community leafed through it and said, oh, there's no mathematics here, there are no diagrams, this doesn't look like a college textbook. I have nothing to learn from this. It's talking about wild and exciting developments. It must really be a piece of science fiction. And so they dismissed it. So there was this very strong polarization in the community between people who understood it and thought it made sense, and those who didn't and thought it didn't.
One of Drexler's early ideas was the meat machine. He reasoned that at the molecular level, a cow was just a machine that rearranged the atoms in grass and a bit of water and turned them into beefsteak. His proposal was that it would be possible to construct a machine that did the same, only far more efficiently. A solution to the world's food problem and the replacement of agriculture in one fell swoop. It's not surprising that most scientists took his ideas with a pinch of salt. Distant as Drexler's visions sound, most scientists now believe that nanotechnology is at least technically feasible. Nanotechnology is becoming a respectable area for research. One such project has recently begun at the Xerox Corporation's Palo Alto Research Center.
Well, this is basically a new manufacturing technology, so it lets you build things. Take this chair. This chair is rather heavy, clunky, rather lumpy. If you were to build that chair out of, for example, diamond, then it would be much lighter. Diamond has a strength-to-weight ratio over 50 times that of steel. And if you were to use intelligent materials, it could adapt. It could conform to your shape. You could have a chair that would luxuriously fit you very precisely. Of course, diamond today is a very valuable commodity. I mean, this costs a lot of money. But it's not because the elements in this are rare or scarce. Now, gold, there the elements are quite scarce, and so gold stays valuable even if you rearrange the gold atoms. But this, the reason this is valuable is because of the way the atoms are arranged. If you took the carbon atoms in a pencil lead and rearranged them into this structure, then you could make something that was quite valuable by today's standards simply by rearranging the molecular structure. I mean, diamond is a material scientist's dream material. It is stronger, it is lighter, it has better optical properties, it has better semiconducting properties. You name it, diamond's got it in spades. So if you ask the question, what do I want from my material? Diamond is either the answer or pretty close to the answer.
My guess is that by the mid-21st century, if you see an airplane, its structure won't be aluminum and it won't be graphite composite. It will be diamond or diamond-like materials. If you see a car, and that car is made out of light, strong materials, as it should be to be safe and fuel efficient, it will be largely made out of diamond or materials like it. So, yes, I think that we are moving toward, in the sense that we've been in the Stone Age and Iron Age and the Steel Age, that we're moving toward what is in effect the Diamond Age, or a diamondoid materials age.